So you have an inverter, you have a NOR 2 gate, you have a NAND 2 gate, another inverter, and then you have a load capacitance. Okay, this is the example that we have, and let's assume that this capacitance is a 1x capacitance and this capacitance is a 45x capacitance. Okay, can you go ahead and solve and tell me what the minimum delay is in this circuit? Okay, tell me what the logical effort is for each of these gates. 1 NOR 2 5 by 3, NAND 2 4 by 3, again inverter 1. So what's the path logical effort? 20 by? Okay, great. The of course the electrical effort is what? Variable shown here, x1, x2 by x1, x3 by x2, right, and 45 by x3. Path electrical effort of course is just output capacitance by input capacitance, that's all. Okay, you don't have to do this multiplication always. Path electrical effort is just output cap by input cap is nothing but 45. What is the parasitic delay? 1. What about this? NOR is you count the output capacitance, right? So what do you have? 4 plus 2, 6 by 3, that is 2. Now this NAND 2 is also 2 because it is 2, 2, 2, right? And again this is 1. So is summation Pk is nothing but 6. Okay. What is the path effort? It is G into H. 20 by 9 into 45. So you get how much? 100. Right? Now therefore, the optimal stage effort is F power 1 by n. And therefore you will get how much? 100 power 1 by 4, right? So you get about root 10, which is approximately what? 3.14, let's say pi. So this is the optimal stage effort that you have to get, which implies minimum delay is nothing but n into f power 1 by n, because the delay of each stage is now f power 1 by n into f power 1 by n plus p. How much do you get? 20, because you get 3.14 into 4 plus 6, about 20, is it? Yeah? 18.6, it doesn't matter. Okay, this is the minimum delay. So now what you can do is, you can go step by step and solve for the X case, so that you can find out what the capacitance is. Okay. Now each Fk has to be 3.14 3.14. Right? Maybe I should just go back and do it there. Makes it easier. Here, Fk, stage effort is G into H. Therefore, this is x1. Right? This is equal to G into H, by the way. So, I am just multiplying G into H. You get x1. This is 5 by 3 times x2 by x1. Right? This is 4 by 3 times x3 by x2. And this is just 45 by x3. Now you can start from either side and start solving for each variable. Each of these Fk's should be equal to that optimal number that we got. Each should be equal to 3.14, which implies x1 should be 3.14. Right? Can you calculate x2 for me? Yeah? Then we have 5 by 3 times x2 by x1 equals 3.14 again. Right? Therefore, x2 is 3 by 5 times 3.14, 14 into x1, which is nothing but 3.14 again. So, pi squared is 10, you get approximately equal to 6. Right? You will get this as 6. Similarly, you can solve for x3. Right? x4 by 3 into x3 by x2 equals 3.14. Therefore, x3 is 3 by 4 into 3.14 into 6. So, how much do you get? 13? 13.93. Now, please check that the final calculation also gives you the same answer. Otherwise, you have made a mistake somewhere. On the last stage, we have the load capacitance x4 by x3 should also be equal to 3.14. But now x4 is known. It was 45 and this is 13.93. So this is approximately seems correct. Right? We have made some approximation of root of 10 is pi, therefore some small error might be there, but you should get approximately this to be the same. And therefore your answer is correct. Okay. Now the next step is to figure out what the size of your NMOS and PMOS transistors are. Right? What we have found is the total input capacitance Xk. We have solved for each of these things. I now have to divide this amongst my NMOS and PMOS transistors. Correct? So that has to be done as follows. So you take the NOR 2 gate, I have a capacitance here, and we said that x2 was how much? 6, is it? Yeah? 6. So I'll first find out how much the gate has been upsized by. Okay. So if this is a NOR gate and it has been upsized by a factor of K1, then what is the capacitance at the input? Unit gate gives 5C. 5 K1C is my total capacitance. So I can say 5 times K1 into C is equal to 6. Therefore, K1 is nothing but 6 by 5C. But what is 6? We said that the unit, should be, oh, x1 is it? That's the variable that we use. Oh sorry. No, sorry, you're right. x1 equal to 3.14. Okay, 3.14. But what is 3.14? We said it is the capacitance gets scaled based on the unit inverter's capacitance. Right? If this was 3C, then x1 is 3.14 into 3C. Right? So that we are going to incorporate now. Into 3C implies K1 is whatever value you get, 18 by 5. This is what, about 3.6. Yeah. So like that you can find out how much the gate is upsized by, or in the tutorial you will see that I will now change this normalizing capacitance. Instead of 45x, I will say that the capacitance is equal to some 100 lambda of width. Okay, it is some 100 lambda of width. So if the unit capacitance, if a unit transistor, right, gave a width, has a width of 4 lambda and that has some capacitance C, then I will say that this load capacitance instead of 45x can be some 400 lambda of width. I'm just giving different ways of normalizing this capacitance, that's all. So then in that case what you have to do is, you have to look at this unit inverter's capacitance as follows. If this is 4 lambda by 2 lambda and 8 lambda by 2 lambda, then the capacitance that this inverter is offering is equivalent to 12 lambda of width of capacitance. With regard to that, I am telling you that there is 400 lambda of width there. So you can solve for this, in different ways. So it's just a question of getting used to the style of problem, that's all. Okay. But all I'm saying is, after you find the minimum width, you have the extra step of finding out the sizes of these transistors, or the how much the gate has been upsized by. You have to do that extra step. Yeah. Yeah, because that's how I've defined the capacitance. When I said that x1, you look at here, I said x0 was 1x of capacitance. That's why I said that the electrical effort is 45 by 1. Output capacitance 45 divided by 1. But how much is 1x of capacitance? It is equivalent to 3C of capacitance. So you have to be careful about this normalizing constant that we are using. And do it consistently across all the gates. It doesn't matter how you normalize, but you have to do it consistently across all the gates. That's all. Yeah. So usually that kind of ambiguity will not be there, because like I told you, I will move to the giving you the width of capacitance. This gate gives you 10 lambda of capacitance, or the load capacitance gives you 100 lambda of capacitance. So there's that ambiguity will not be there. don't worry. Okay, I just started with 1x, 2x in my earlier discussion. I continued with that, and then we'll move to that other normalizing standard. Okay. So now I will leave you with an interesting problem where in the same problem, just solve for the load capacitance being 4500x. Can you tell me what the minimum delay of this circuit should be? Yeah? You get a capacitance of 40. Okay. So what is my path logical effort? Again, it is 20 by 9, no change. Electrical effort is load capacitance by input capacitance, and this we made it 4500, which implies that path effort is GH, and this is nothing but, what do you get? 10,000, 10 power 4, implies min delay is n into f power 1 by n plus p. Okay, so this is 4 into 10 power 4 by power 1 by 4 plus 6. So it's not just 40. Huh? You get 46. 46. Okay. What was the delay we got earlier? Minimum delay? 18 point something. Okay. Now the delay of this circuit has gone up significantly. Right? Question is, can I do something in order to bring this delay down further? Okay. Now, what is the stage effort, by the way, for this circuit? Equal to Fk is f power 1 by n. What is this? You get a stage effort of 10. Okay. So in some sense, each stage is having to do a lot of work. Earlier, the stage effort was somewhere near 3. And that's why the delay was reasonably low. The problem is now if my stage effort goes to 10, 20 and all that, I have a problem. Each stage is now doing too much of work in order to minimize the delay. So the fundamental problem here is the fact that my n is a very small number. I have a logic circuit that I made which had one inverter, NOR, NAND, another inverter, right? So effectively I just have 4 gates in the path and I am trying to drive a very large load capacitance of 4500x or even larger. If you do that, then I have a problem where each gate is having to do too much of work even for the minimum delay. Remember, this 46 is indeed a minimum delay. It is a minimum delay given that there are only 4 gates on the path. So the next problem that we will be solving is to do better than this. Now, how do you reduce the effort on each stage? By increasing the number of gates on the path. What can I add on the path? I got to add buffers. Okay, let's assume logical inversion I will not worry for now, right? Yes, you're right, I have to be careful about that because I have to add inverters on the path. But why will I add an inverter? Why not an AND? Yeah? Anything other than an inverter has an NMOS or a PMOS stack which is greater than 1, and therefore the logical effort is higher than 1, which implies that the delay will now only increase if I put any other gate other than inverters. By adding inverters on the path, I don't change the path logical effort. I can add any number of inverters. I take this circuit here and I can now append to this as many inverters as I want and then move this capacitance here. Of course, I can add as many inverters as I want, but the path logical effort will not change. Neither will the path electrical effort change, because path electrical effort is still output load capacitance by input load capacitance. But what this has allowed us to do is to increase the number of gates in the path. My N instead of 4 is now becoming something like 7. So this path effort that we got of 10,000 will now become 10,000 power 1 by 7 to give me a stage effort which is much less than 10. That 10,000 power 1 by 4, I have made it 10,000 power 1 by 7, and therefore reduce the effort that each stage has to put in minimizing the delay on the new circuit. Okay, this is the problem of buffer insertion, and we will do this tomorrow in the class after the quiz. First 20 minutes as usual will be a quiz, and then we will solve this buffering problem tomorrow in class. Okay.